Hello, this is Tim here. I hope you're doing well. This is going to be the first video in a range of videos on electro-pneumatics. Um, so yeah, strap yourselves in. Um, I'm a big I would say I'm a big fan of pneumatics, but I definitely enjoyed them when I was in college, and I do find them to be very useful. They're useful and they're inexpensive and they're safe and they're very easy to control. So they are you know they are one of my favorite. They're not one of my favorites. That's it's where I'm talking about movies or something. But look, pneumatics and electro pneumatics are useful things, and they're not that hard to understand. So it's a positive thing. So don't be scared of it. Um, the first thing that I'd like to show you is an actual mechatronic system. This is something we designed years ago, but um, we used pneumatics a fair amount in a couple of the systems. So I'm just gonna show you it working, and then we're going to talk about why certain systems are electrical and why certain systems are pneumatics. But let's start at the beginning. What is a pneumatic system? A pneumatic system is takes compressed air and does something with it. Hydraulics takes a compressed liquid, typically hydraulic oil, and does something with it. Pneumatics, why would you use one over the other? Um, if I want to move something quickly that's not incredibly heavy, pneumatics is like a door on a train. Pneumatics would be better for that. Pneumatics are cleaner than hydraulics. Now, a wood splitter. I don't know if you've ever seen a wood splitter, a hydraulic wood splitter. I could be wrong here now, but I don't think I've ever seen a pneumatic wood splitter. Anything that requires a lot of force is going to be um, hydraulics. Okay, so let me just run. That's the difference between the two of them. Okay, and whenever you hear someone talk about fluid power, they're either talking about pneumatics or hydraulics. If you know pneumatics quite well, or you know hydraulics quite well, it's not that difficult to jump between the two, even though there are important differences. Um, the cylinders are similar, the valves are similar, the gauges are similar, the concept is similar. Okay. Now, in fairness, I've never designed a hydraulics system before in my life, so don't go nuts on the comment section for me if you don't mind. But let's have a look at this. This was a little machine that basically kicked out a cup, different color cup, filled it with Skittles. Depending on the color of the cup, filled it with a certain amount of Skittles. There's a little auger there, and then put it in a little storage area or a little sorting area. Very simple automated machine, but a lot of sensors, a lot of components. It does it over and over again. This white gizmo here in the background is the brains of the system. So let's just run it again and look at it again. Let's see what it actually does. It pushes out a cup. It traverses down here to the next position. There's a couple of sensors there detecting what color of a cup it is. We have a motor turning on for a certain amount of time, and we have an arm that kicks out and then just pushes it in. It looks like we have four positions. Go back there for a sec. Looks like we have four positions on this transfer station. Okay, we have a light tower, we have a PLC, and we have some sort of gauge there. Now, um, so I would have drawn this up and I said, right, I need to kick, I have some sort of gravity fed system here. I need to push something out and I need it to retract. Okay, so pneumatic systems can do linear motion. This is a cylinder. What it's like a piston, but that, if you don't know what a piston is, that doesn't make a whole lot of sense. We push air into one end of the cylinder and its arm comes out. we push air into the other end of the cylinder. What the hell am I even talking about here? This little barrely looking thing. Okay, the barrely looking thing has a little something connected to it, and it pushes out and it pushes back. That's an example of linear motion. Here we have an auger and it's being controlled by a motor. That's rotational motion. Right here you can see the little gear here. Okay, here's another example of linear motion. Okay, now to confuse even more, here's a motor that's turning an Acme screw that converts rotational motion into linear motion. So your heads are probably melted. All right. Anywhere I have, now let's go back a little bit. Electric motors can do rotational motion quite well. They do not translate into linear motion. They require a few extra components to turn that rotational motion into linear motion like we have down here. If I have to do any sort of linear motion like punching out and back, out and back, out and back and so on, my brain is telling me a pneumatic system will be better. Okay? So we have two pneumatic systems here, unless I'm brain dead and I can't think of anything else. No, there's two of them here. It pushes out and comes back. This one pushes out and comes back to bring it in place. Creating an electrical system to do either of these is doable. Hopefully, you know, if we were going to do something like that, what would we do? We would use a rack and pinion for something like that. Okay? So these are pneumatic systems on either side. In the middle is an electrical system, and this is an electrical system. We combine it all together with a PLC and we have a mechatronic system. So hopefully that hasn't scared you away. I like pneumatics. I really do. I think they're clean, they're fast, they're cheap. The components you get them from Ally, you can get them from McMaster Car or Automation Direct. Automation Direct is even cheaper. So here we go. In that system that I showed you, this is called a cylinder, a pneumatic cylinder. It has two ports coming into it. You can't see it here, but we would connect that blue tube to a compressor. Okay, so we have a compressor. Now, what the hell is a compressor? Have you ever blown up your tires at a gas station? There's a compressor there. It's the thing that makes the big racket. And it basically takes the atmospheric air that's around you, compresses it into a small little reservoir, and Bob's your uncle, we've compressed air. We've compressed air here that comes in. This is a gauge. This is a pressure gauge. We can turn the pressure up or we can turn it down, and you can see there's a gauge here that shows it. This is basically, honestly, this is basically all the components of a pneumatic system. Okay, we have a pressure gauge. The air comes around there, you can't see it. It comes into some sort of valve. Okay, this is a valve. It basically, what this valve does, it either gives the air into the A port or it gives the air into the B port, and that's it. Okay, now right now what it's doing is I can see, and then air comes round here to this cylinder. These little black things with the little screws on them are ports, but those little screws are called flow control. What that means is it controls the speed of how fast this thing comes out. Okay, now pressure and speed are different beasts. Okay, this thing could come out very, very quickly, like lightning fast, but I could put my finger there and stop it. No problem. It doesn't have a whole lot of pressure. It doesn't have a whole lot of force. Or it could come out really, really slow, and I could try and put it in a vise, and the vise ain't going to stop it. Why? Because it has lots of force. So the first thing is there's a difference between speed and pressure. Okay, we're going to get into that later. You might be able to see some electrical wires coming here. This is an example of an electrically operated valve. It's the voltage coming in here that's turning on that. This thing isn't manually operated. There's no button here we can press that will switch it. Okay? So these are the main components. You're done with the class. You can go home now. You got an A. Alright? You have, no, I'm joking. A pressure gauge, a valve, and the cylinder. Alright? FluidPower uses fluids under pressure to generate, control, and transmit power. We'll talk about that. We'll talk about this a little bit more. It's similar to electrical power, and each version of the FluidPower has its cousin over on the electrical side. It's divided into hydraulics, such as hydraulic oil, and pneumatics, which use a gas such as air or other gases. I've never seen or heard of pneumatics. It's always air. Now, if anyone has an idea in the comments, that's fine too, that uses another gas. I like pneumatics over hydraulics. Why? Hydraulic oil is messy, and whenever I've used hydraulics, I always get it on my clothes. Hydraulics is a lot more force. So, I don't know, do you know, I have been told of former students and graduates, whenever a hydraulic line would burst, it's like it cuts like a knife. So that's not a place I'd want to be. So I would hope that you're going to get more training in hydraulics if you do end up working on a hydraulic system. But pneumatics are in my opinion, easier to use. You wear your safety glasses around them. Okay. I think I've covered this, but the difference, if you're moving heavy loads, hydraulics is the way to go. The pneumatics, if you have a situation where you cannot, where pneumatics will compress, it compresses, and what does it do? When would we need this? When would we be in a situation where we cannot have an arm or something that's not compressing? If you're crushing something like rocks, or if you're splitting wood, if you're lifting something really heavy, you do not want that arm. If you want that arm to move, you need all that force there. I'm not explaining that very well. It does have a smoother motion. Why? Because you cannot compress a liquid, and it is precise. Fluid does not absorb energy, it's non-compressible, and it self-lubricates. With a pneumatic system, you do have to introduce some oil into it, into the actual air, to keep it lubricated. And with pneumatics, you have to remove you want to try and remove water from the atmospheric air. So we use dryers and stuff like that. We'll get into that later. Don't get hung up. Don't get hung up on this. Yeah, a jerky spring-like motion, because the air can be compressed. It is less precise. The compressor is loud. But if you have a nice expensive compressor like we have in our lab, made in Germany, it's pretty quiet. It's only useful in relatively low PSI operations. Alright? So, in a fluid power system, you have the compressor. The compressor compresses the air. It goes via pipes to a, what are you doing? To a valve. The valve can change directions. It goes to another pipe, and then it goes to the cylinder. That's where it actually does the work, whether it be opening up a door, whether it's an arm that's lifting something up. I don't know. It could be anything. Now, what is the electrical analogy of this? The compressor is like the generator, an electrical generator or a battery. This is the source of energy. The pipes. Now, what do you think the pipes are? The pipes are the cables, the electrical wires and the electrical cables. Now, what is the valve? The valve is, if we want to switch the direction, is the relay. Now, you probably don't really know what a relay is, but we can provide, the electrical relay can provide power to one cable, or it can provide power to another cable. Maybe a switch. A switch is the equivalent. What is the equivalent of a cylinder in an electrical? You might know what a solenoid is, or it could be a motor. A motor actually does some work, an electric motor. Okay. Now, what we're going to do in this class is we're typically going to, now what is, first of all, what is this? This is a schematic, and you might have seen electrical schematics before. This is a pneumatic schematic. All right, pneumatic schematic. Now, what we're going to be doing in our class is you're going to be drawing up pneumatics schematics on something called Fluid Sim. Okay, now where the hell is Fluid Sim? Here you are. You're going to have this on your computer, and you're going to be able to draw up all these funky, beautiful schematics, and then you're going to be able to run them, and you're going to actually see how the air flows on your computer. And then once you're done with that and you know what's going on there, then you're going to build the real pneumatic system in the lab with me. All right, and we're going to test it, and I'm going to be a dick, and I'm going to unplug stuff, and I'm going to intentionally wreck your system, and then you're going to troubleshoot it. Okay. Now, these are all pneumatic symbols. This is the symbol for a cylinder. Okay, that if you put air in here, the piston comes out and blah blah blah. This is the symbol for a flow control. Don't worry, you're going to understand how all this works. This mad looking thing is the symbol for a directional control valve, or a valve, and then this is the symbol for a pressure valve. Whoops. And this thing down here, this little triangle, is a symbol for a compressor. Now, yeah, we talked about this, but this is a better picture of the pneumatic system that I showed you. All right, and this is the valve. It has two tubes that are connected to the cylinder, one at either end. If this thing was coming out and back and forth like Bruce Lee, we would tighten those screws up there, and we'd be able to control it and come back nice and slow. Or we can change the speed with these two little valves. That's all they do. All right. Now, the blue tube that comes around here goes off to the pressure gauge. You can't see that, and then it goes off to a compressor. All right. So here is a little slide on a hydraulic system, and I just want to show you that the differences between a pneumatic system and a hydraulic system. This portion that I don't know if you can see this, I don't know, hopefully you can see, oh, here we go, that'll work. This portion would be our compressor, okay, but with a hydraulic system it's a little bit different. We have a motor and we have a pump, and all the pump is doing is it's trying to force that hydraulic oil. It's basically it's adding pressure. It's adding pressure to that hydraulic oil. Okay, this is the inlet of the pump, and this is the outlet. Now, the oil is under pressure. Okay, and it basically comes around here, goes back into a reservoir, and it's just continuously under pressure here because of the piston and the power source. And if it wasn't, the pressure gauge would be very, very low. If this motor is spinning, this pressure is going to increase. Okay, this is our valve, and this is our cylinder. The valve is controlled by a manual arm, or a knob. Now, this valve here is when the knob is in its home position, it's not doing anything. Okay, the valve has three positions: 1, 2, 3. If I push the arm in this direction, what it's going to do, this whole block here is going to shift over, and the pressure is going to come in through here, and it's going to come into my cylinder, and it's going to push out, and so on. If I push the arm back down in this direction, this little box is going to come into the middle, and then the hydraulic oil is going to crisscross over into this section of the cylinder and push this back. I'm going to show you this in a video in pneumatics, and it'll make more sense. What is the difference between a hydraulic system and a pneumatic system? The hydraulic system, it has a return loop. The oil always comes back into the reservoir, into the two-stage pump. With a pneumatic system, the air is just exhausted into the atmosphere. I don't know if you're going to understand that. You don't get too hung up on that. This is a class in primarily electro-pneumatics. Okay, so your air is going to exhaust out into the real world, but with a hydraulic system, it's kind of a closed loop. Okay, if the hydraulic line, which is not just a simple tube, it's a lot more robust, was going to pierce or get cut at any place along here, that's a bad sign. Okay, that means hydraulic oil is going to be put out under pressure. You don't want to deal with that. You need to be very, very careful. Okay, now I had a nice video that I stole from somewhere that kind of explained the safety of pneumatics, and I'm going to just explain it. I don't think it's going to work. If a pneumatic line comes off or under pressure, what it will do is it will come out of its port, and it will flop around really, really fast. The danger with that is if your eye is anywhere near that pneumatic line, it comes out at speed, it could hit you in the eye, and it could injure your eye, which would not be a pleasant thing. So if you're ever working around pneumatics, you should be wearing safety glasses. That's number one. The other thing with compressed air is you do not want to blow compressed air anywhere around a cut or anywhere around a body opening, like your nose or a mucous membrane. I don't even know what the hell that means, but around your mouth or around a cut, it can cause a blood clot. Now, that sounds like a bad thing. I don't know if a blood clot is a good thing, to be honest with you. But keep the bloody compressed air away from your eyes and away from any open cuts. I've been told. Okay, that sounds like good advice. All right. Right. So I'm gonna run into this this control of a single acting cylinder. Okay. Now this is a nice little cross section of what a cylinder looks like. Now, at this stage, you should have an overview of what pneumatics is all about. But now we're going to talk about how we would actually control a single acting cylinder to open up a door, to I got to come up with better examples. Move an arm, to lift something up, to imagine you have a conveyor belt that's pushing boxes down a conveyor belt at speed, and we want to push a box off into another conveyor belt that's sending packages to Tim's house. You could do that with an arm, and connected to the arm would be a cylinder. Okay, now look here. The air comes in this port under pressure, and what do you think it does? It comes into this little cavity, and this cavity, this is our piston. Okay, it comes up to this piston and says, "Oi, I'm the boss now. You need to push your way down here to as far as you can go." And that's what it does. This little spring here that's in this cavity gets compressed, and the arm comes out. Okay? This little blue bad boy is a seal. And what that does is it stops the air from coming through and bypassing the piston. Okay? Now, if I turn off this air, or I turn off the air coming into the cylinder, the spring is going to come up and it's going to say, "Well, I'm in charge now. I'm the man. I'm going to push this piston all the way back and it's going to win, and it's going to push this air and that air will be exhausted. How do we know this is a single acting cylinder? There's two things that are my brain looks at. Let's go back here for a second. I can see a spring inside of it and I can see only one port. Okay, if it had two ports, it would be a double acting cylinder, but it only has one. It's a single acting cylinder. All right. We're going to talk about pneumatic symbols. You're going to learn how to control a single acting cylinder with a 3-2 valve. You're going to simulate the pneumatic circuit using the Fluid Sim software. And if you were with me in real life, we're going to construct a pneumatic circuit that you've just drawn up in Fluid Sim. All right. Now, why do you need to know about pneumatic symbols? You're going to, hold on a second, I'm going to pause this for a second. I'm going to show you a pneumatic diagram. I want you to imagine down the road that you're in a local company and you're the main person to troubleshoot the whole mechatronic system, and for whatever reason your brain is telling you there's something not right with that pneumatic system. Okay, the arm is coming out, it's hitting people, it's coming out too slow or whatever, it's just not working very well. What you're going to want is you're going to want a schematic of the whole system, and that's what you're going to see here. This is an example of a pneumatic system. Now granted, it's wrecking my head a little bit now, I've only been looking at it a little, but you need to know what each of these symbols do. Okay, now my brain can say, well, I know that's some sort of a valve, I know this is some sort of a valve, this is some sort of a pressure gauge, this is some sort of a manual control, you know, and I could with enough hair pulling and enough hemming and hawing, I could probably look at this and understand what's going on. So trust me when I tell you, you need to understand what the different pneumatic symbols are, because you can actually understand how the symbol works. Okay, now this is a symbol of a cylinder. This is a symbol of some sort of flow control. This is a symbol of a valve. And this is a symbol of, that is called, I know what this is called. It's called a filter, an FRL, a filter, a regulator, and lubrication. Maybe. I'm not sure. We'll worry about it. So these are symbols of different components. And you can see here, the air comes in here and it goes through each of them, just like an electric system. Okay? Now, what is the symbol of a compressor? This is a two-stage compressor made by California Air Tools. I'm just reading it out. This is the reservoir, okay? And this is where it's connected to. The compressor that I like, it's called an air service unit. That's what the hell that thing is, all right? Now, the supply elements, a little triangle is called a compressor. An air service unit. Now, what does an air service unit do? Let's look at it. Air comes in here, and it looks like, what's nice about the symbols are you don't have to think too hard about it. I want you to, I'm in a room right now, my bedroom, and believe it or not, and how big is that? What is the volume of the bedroom? It's about 20 feet by 20 feet by about 10 feet air. I have a nice high ceiling. So what is the volume of that? It's 20 by 20 by 10, which is, what is the square footage of that? 20 by 20 is 400 by 10 is 4,000. Would that be right? 4,000 cubic feet. And when you compress that much air, atmospheric air, it has, look, let's find out for fun. Let's find out for fun. Let's go to Google and I'm going to type in 20. Let's see what comes up. Presidential pardons, never mind. Never mind. Stock sec. These are not my, I don't search for boring stuff like this, believe it or not. 20 by 20 by 10. 4,000 cubic feet. So what if we wanted to find out how much water, I'm going off on a mad tangent here, in air, cubic air, 9 grams of water in a cubic foot of air. How much water, moisture in the atmosphere? Come on. Give me some sort of brain dead calculator. Let's do this. How much of calculator in one cubic foot? Oh, this is a pain. I'm going off on a mad tangent here. Look, let's go back. Trust me when I tell you it's amazing how much water is in the air. You know how much in a hot summer's day when the humidity in Maryland is bad, and if I actually had hair, your hair would it gets very, very sticky. All right, now trust me when I tell you there's loads of water in air. What this thing does is it is a drain, a manual drain, and what it does is it filters out some of the water, and you can drain some of the water out of the pneumatic system, because we don't want the pneumatic system to get rusty. This next thing is a pressure gauge. And I know it's a pressure gauge because I can see some sort of a spring here with a line across it, an arrow across it, which means I can adjust this spring. When the spring gets too much, it lets the pressure out, and that's what that's doing there. It lets it out into air. Does it tell us anywhere there, air pressure? What this is the symbol for is this little portion is the symbol for the little pressure gauge. We'll get into that later. It comes round. Okay. So this is the air supply. This is the air preparation. Does that what it says here? No. This prepares the air for the pneumatic system. This is the pneumatic valve. Right here, this is a two-way valve. Okay, it is two positions. This is one position, and that's its second position. Okay? This little button here tells me that that's a manually controlled valve. On this side, it's a spring return. Okay, so when my finger presses this bad boy goes over to here, and the air goes through. You're going to see it in the nice fluid sim. It goes through here into the flow control, and then it comes in here into the spring, the one-way valve. It gets kicked out, and then when my finger comes off of here, the spring pushes it back, and this air is going nowhere. It's coming here, hitting a brick wall. The spring comes back in and say, here, I'm in charge now. It pushes the air out. The air comes back around here. This ball will get pushed out of the way. It comes back down, back into the atmosphere, and everybody's happy. Okay, so these are the different symbols that you need to know. The drain looks like, you can see the air comes in here, and you can see the little puddle of water, and then the water comes out. The lubricator, which is dropping oil into the system, comes down from the top. Okay, I've never really seen any of these other symbols. A symbol for a cooler, we'll talk about that later. All right, now air service unit, or an FRL. I don't know what the hell I was thinking. A filter, a regulator, and a lubricator. So this is the air service unit, and it combines all of them. This is a nice one. So this is the drain. This two together is our pressure regulator, which you're going to see in the lab. And then all this is doing here is this is just a little on and off. So we could just and I'm guessing this symbol is a detent. Is that the right word? It's not. Oh jeez, me brain. It's either Never mind. I'll come back to that later. So this is the air preparation. So we would connect this to a compressor, and then this would go off to the next stage. So I want to talk about this just a little bit more. So this, even though this is the symbol, this is what it looks like in real life. This gauge here tells us how much pressure is on the line, which is this symbol right here. This section here is, and I've never seen this type of FRL before, but I'm guessing, because I'm guessing this is the drain, and what this does is it tries to remove as much moisture and water from the system as possible. And I can open up this drain, or I could connect it to the water drain or the drain itself, wherever that would be. And we have input and output ports. I don't see any on-off control on this. This handle here, or this knob, represents this section here. We can turn this up full blast and have loads of pressure down the line, or we can turn it really, really low and have only a little bit of pressure down the line. So that's what that is. That controls the pneumatic pressure. So when in doubt in your system, keep this chap really, really low. All right. Now, the next section is, so this controls the pressure. That's how much force the arm can come out of. Flow control is different. Speed is a different thing. Now, what is a good analogy, a good mechanical analogy for this? I want you to imagine a DC motor. You might have had one in your hands before, a little DC motor spinning really, really, really fast. And it sounds like this. Bzzz, all right? And then I want you to grab it with your finger. And you'll notice the little DC motors you could stop with your two fingers, between your thumb and your forefinger. Okay, I want you to imagine a big DC motor. And I want you to imagine it spinning really, really slowly. And it's moving round and round. And I want you to try and grab it with your hand, and there's no way you can stop it because it has too much torque. Torque is like pressure, and the RPM of the motor is like the speed. Okay? So it depends on your application. Sometimes you're going to want the arm to come out with a lot of force, a lot of pressure, and you're going to want it to come out nice and slow. Or you might need it to come out fast, and you might need it to have a lot of pressure. It depends on the application. Okay? These three gizmos can control the amount of speed. Okay? Now, this has two ports, and this is called like a quick disconnect. You can just feed your tube into here, and you can feed your tube into there. If you want to take the tube out, you push that little blue ring in and you pull the tube out at the same time. What this has, it comes in here through here, and inside of this there's a little cavity, and the cavity gets bigger or smaller depending on how much you turn this little thumb screw. We could open up this thumb screw and the cavity will be nice and big, or we could close the thumb screw and the cavity will be really small. What this bad boy is like in real life, it's like a resistor. Okay, now God help you if you don't know what a resistor is, or there's lots of videos on YouTube that can help you with that. This is a resistor, okay, to control the speed of the flow. Again here, the input's coming in here in this example, and it has a quick disconnect on this side. And why does it have two screws? Because you can set it at one place and then you turn the other screw back against it, and what it does, it locks it into place. What this thing looks like, the symbol for this bad boy, is it's either one of these two. Okay, now let's look at the easier one first. What this does is it has two ports, and you can see here this is called an orifice. Okay, and it's just a tube. But what we can do is we can control the diameter of that tube, and that's what that arrow indicates. Whenever you see an arrow indicating like that, it means that it's variable, and it means that you can control it. Lovely. Okay, So if air comes in this direction, it's going to go through that orifice to the other side, and when air comes back in this direction, it still has to go through this orifice. So this little flow control controls it in the same in both direction. Okay, now this is called a one-way flow control. Okay, I know your heads are getting melted. What it can do is, if air comes in through this way and it tries to go through this, it's blocked. There's a ball here. Do you see the ball? And the ball stays. It's not coming through. It's blocked. It's hitting a brick wall. So it has to go through the flow control. This is called a one-way flow control. And it's going to come through this way and it's going to do its thing. If air comes back through this way in the reverse direction, it could go through the orifice, or it could go this way. The ball will get out of the way and air will flow that way. You're going to see that later. Okay? If this is confusing you, it's going to make more sense when we're doing fluid sim. All right? Now, if your head is melted, I want you to just take away a few things. You should know what the symbol for this is. It's a compressor. This mad looking thing is a valve. Okay, you will understand what each of these does later. Okay, this is how the valve is actuated from this direction, and this is how the valve is actuated from this direction. You can see here air comes in. You can see air is going three places. Don't worry for the time being. So this controls the air. This controls the speed of the air, the flow control, and then this is the actual valve, sorry, the actual cylinder itself. This does the work. This is the thing that's connected to the arm or the door or whatever. Someone comes up with a better example in the comments section. Now, it's very important to label every component. The lady that I work with, Peggy, says, Tim, you're forgetting to put labels on things. Labels are important, and they are important. Now, every component needs to be labeled. Why? Because you're going to be in a local company and some person is going to be complaining about something that's not working, and they're going to say, well, Patrick, why don't you look at the directional control valve? What directional control valve are you talking about? 1V1. You're going to have loads of these valves. You're going to have loads of these flow controls. Each one of them needs to be labeled on the document so you can communicate with other people. Okay? Everything needs to be labeled. I'll get into that later. Whenever you label a cylinder, it's always 1A1. Valves are 1V1. I'll get into that later. Okay. So these are your cylinder symbols. Okay. This is, you can see air comes in here, pushes the piston out. This is a single acting cylinder. Okay. This is a double acting cylinder. We have ports on either side. So air comes in this way, it pushes it out. In order to retract the cylinder, we have to put air in this side. How does this retract? This bad boy, this single acting cylinder doesn't need air from the other side because it retracts under the force of the spring inside of it. Okay, this chap is called a rotary cylinder, and instead of it just being linear, we can put air in one side and it spins. It pivots around this point. You know, rare enough. I haven't seen one in real life, but we do have them in the college lab. This bad boy is a single acting cylinder, but what it is it's a normally actuated cylinder. There's probably another word for that. It's the opposite of this. So its home position is extended. It's a naturally extended cylinder, and it takes air pressure to retract it. This this symbol here, we're going to talk about that later, but that controls that it's it's an adjustable damper. And what you can do is, instead of this, if we put air here, what it does is it will come out, and as it gets close to the end, it decreases, it slows down in acceleration. That's what that controls is. So it doesn't come out full blast and in full blast. It comes out as quick as it can, and then it's like an elevator. It once it gets to its destination, it chills out and it slows down. This is important. Okay, so we're going to talk about control valve symbols. Okay, now you're going to hear about what we call this, a valve or a control valve or a directional control valve or a DCV. Okay, and this controls the flow of the air, not the speed or the pressure. It controls the direction, a directional control valve. This is called a 3-2 valve. A 3-2 valve. Okay, and what the first one is, a 3-2 is each one has 3 ports. 1, 2, 3, and then it has the 2 squares, has the 2 positions. So we'd call this a 3-2 direction control valve. And look, even though I've been doing this for years, I still have to think about it. Okay, now so what is this? This is a 3-2. So each section of it has 3 ports, okay? And it has 2 positions. So this, I would call this its home position. When it gets actuated over here, this portion gets pushed over, and now it's actuated. Okay, so you're going to see that now. How does it get actuated? It could get actuated manually by a push button. It could get actuated by a mechanical limit switch or something. It could be actuated actually by pneumatic air coming in here and pushing it. The most common is electrical. So some sort of a solenoid that pushes it over. And then a lot of them are combinational. The most common one is an electrical and manual. It has a manual override, but it has a button. Now, let's have a look at this one here. How is this thing actuated from one side? It's actuated by, this is the symbol for a push button. On this side, it returns, a spring will push it back. So it's a manual on one side and mechanical on the other side. Let me ask you this, could you have springs on either side while I drink my Spindrift? No. This is its home position. When the button gets pressed, basically right now, port 2 and port 1 are connected. If I have air going in, forget about the arrow, the direction of the arrow, it doesn't matter. If I have air going in here, it's going to go all the way to 1. If I have air coming into 3, it's going nowhere. Once I push the button, air coming into 3 is going to go to 1. You can see how it's connected, okay? Now, these are the symbols. Whatever is on this side of the valve is how it's actuated. Whatever's on this side of the valve is how it gets returned. Okay? Now, this is... No, this is the symbol for electrically actuated solenoid. Okay, that's its symbol. It's a dash. It doesn't make a whole lot of sense, but basically what it is it's a solenoid that moves it over. There'd be no harm. I don't want to get into really what a solenoid is now, but it's basically an electromechanical device. You run electricity through it and it pushes it over. There's your manual override. You could have them stacked on top of each other. It will be a manual override and an electrically actuated. This is the symbol for pneumatically actuated. So the thing gets pushed over. This is going to make a lot more sense when we're actually doing it on Fluid Sim. So I just want to go through this quickly. This is a symbol for electrically actuated, a direct actuated valve. I don't know what that means. We'll get into that. This is your spring reset, which is the most common, or it could be a solenoid on the other side. Look, what do I want you to take away from this without it? I want you to understand that the symbols on either side of the DCV give you They tell you how it's actuated, and it's important that you know that. Okay. We can look at this later. This is your component label, how you want to label a cylinder, how we want to label a valve, a sensor, a signal input, and so on. I don't remember this stuff off the top of my head. I just have to go back and reference it when I'm creating a drawing. Forget about this. We're not going to go into this. That's not true. The Europeans and the Americans we do things differently. This is the labeling for the ports. In the Europeans doing it. This is the labeling for the Americans. You're going to see both. Don't get hung up on this. I should delete that. So what we're going to